graphical models, we have Antonio Blanca from Penn State telling us about hardness of identity testing for some interesting families of graphical models.
Hi, everyone. Thanks for the invitation and for organizing the workshop to the organizers. So yes, I'm going to talk about the computational complexity of identity testing in the context of spin systems, and in particular for the POD-SMAL and RBMs, so restricted Boltzmann machines. Okay, so the POD-SMAL was at least defined in an earlier talk for one of the special cases. But let's go through this slightly more general definition. So here we are given a finite graph G, and there is a set of spins or colors 1 through Q. We're also given an edge potential. Essentially, it's a function beta from the edges of the graph to the reals, and this function essentially captures the strength of the interactions between the endpoints of the edges in the graph. And statistical mechanics, this corresponds to the inverse temperature of the system. We also have another function that this one corresponds to an external magnetic field. And in its, again, a general form, it's a function from the set of vertices times the spins to the real number. So essentially, for every vertex, we may have a different vertex potential. And depending on the spin that this vertex is assigned, it gets a different potential. Okay, so now the configurations are the set of assignments from the spins to the vertices of the graph. So we can think of all the Q colorings of the graph. Each Q coloring will receive a probability, and this probability is given by the Gibbs distribution, which is given by this expression here. And essentially, we look at so for a configuration sigma, the probability is given by some weight or some normalization constant. And the weight essentially has a factor exponentially in B to the beta evaluated in the edge, provided that the endpoints of the edge have the same spin, right? So for every edge that have the same spin on the edge on the endpoints, its endpoints, we have this beta of the edge, and then we also go through all the vertices, and there is a factor e to the value of the magnetic field for that vertex and the spin that is assigned to the vertex. Okay, so we saw some special case when there are only two spins. This corresponds to the easy mode, and in many cases we will look at simpler versions of this Gibbs distribution, where, for example, we will assume sometimes that this is just a constant. We always have the same parameter beta, the same edge interaction beta over all the edges, and sometimes we'll look at the case where there is no external field. Right? But this is the most general definition. And as I said, C here is just a normalization constant to make mu a probability distribution, and it's also known as the partition function in statistical physics. Okay, so here is an example. We have Q equals 3. We have 3 spins. The graph here is the 4x4 grid. We're going to assume that the edge potential is just a constant function beta, and then there is no external field. So the probability of this configuration here is given by is going to be e to the 6 beta over the partition function, and that's because you see that there are two red edges here, one green and 3 blue edges. So that's e to the 6 beta. Here in this configuration, we only flip the spin of this vertex here, so we lose 3 of the edges, so 3 of the monochromatic edges. So now you get e to the 3 beta over the partition function. Okay. So as I mentioned, the POD-SMAL is the standard generalization of the classic easy mode to multi-spins. So we allow more than 2 spins. For easy mode, we usually think of the spins as being plus and minus, but we can also think of them as being red and blue, and then it corresponds to this mode when you have just 2 spins. The easy mode is very old. It goes to to the work of Lenz and Ising in the 1920s, when they were trying to explain some phenomena that actually Pierre Curie observed in his PhD thesis, corresponding to some phase transitions of the ferromagnet. So they were trying to come up with some statistical mechanics model to understand this phase transition. They came up with a model that didn't work out very well for them. But then later in the 1950s, the model was shown to actually be quite useful. They were just looking they were just considering the wrong dimensions. They were only considering one-dimensional case. Okay, so since then, yeah, the model got generalized to a Potts model. There are many other standard generalizations and many applications now, not only in statistical physics, in computer vision, computational biology, phylogeny, and it has been also important in computational learning theory. So here is some more definitions and terms I'll be using through the talk, because the model behaves quite differently when all the edges are positive. The edge interactions are positive. This is called the ferromagnetic case. And in this case, the model is attractive in the sense that edges will encourage its endpoints to have the same color, the same spin. And the opposite happens when all this, when beta is negative, then the model is called antiferromagnetic and it's repulsive. So here, the edges will actually encourage disagreements in some points. And another relevant classification here that would be important when we consider the computational complexity of various problems, it's whether the field is consistent or not. And we say that the signal field is consistent when it favors the same spin in every vertex, right? So, for example, in the case of the Ising model, we want a field that the field is consistent when it favors always plus or always minus in the computation. In the Potts model, we want, more generally in the Potts model, we want the field is consistent when it's always favoring red or always favoring green, and so on. Okay. Otherwise, the field is called inconsistent. Okay, so in this talk and in this line of work in general, the goal is to understand the computational complexity of various fundamental problems in related to the spin systems. And yeah, I think the most interesting aspect to me would be to understand the connections, right? Like when one of these problems is hard, what does it set out the hardness of the other? Okay, so let's start from maybe the most fundamental of them, which is the sampling problem, right? So now here we are given the graph, the number of spins, the edge potential, the edge weights, the signal field, and our goal is to produce a sample from the distribution, from the Gibbs distribution, or from a distribution that is close to the Gibbs distribution. Right? So this is a very well-studied problem in empirically and theoretically. For the ferromagnetic Ising model, when, as I remember, ferromagnetic means that the edge interaction is always positive. For the case when there is no field or the field is consistent, there is this classical result of Jerome and Sinclair in 1993, where they show that there is a polynomial running time algorithm for sampling. The running time of the algorithm is a large polynomial on the size of the graph. But unfortunately, this is the best we have right now for general graphs. There have been some more attempts, some more algorithms, very different. They still provide large polynomial running times. The conjecture is that this is doable in sublinear time or very close to linear time, but we are far from proving that. Our progress here has been in providing faster samplers for a specific family of graph, or on the some assumptions, some further assumptions on beta and on H, and on the signal field. Okay. Now, if we now consider the ferromagnetic Ising model, but instead of having a field, no field or a consistent field, we consider the case of an inconsistent field, the complexity of the sampling problem changes. And it turns out that there is no an approximate sampler unless we have an SPRAF for char-Bs. It's a result of Goldberg and Jerome. And char-Bs is this problem of counting independent sets on bipartite graph. And I believe the conjecture is that, the community conjecture is that this is a problem that has an intermediate complexity and plays a role in approximate counting and sampling akin to the unique games in approximate optimization problems or PPAD for the computation of Nash equilibrium. Okay, so that's for the ferromagnetic case. For the anti-ferromagnetic case, the situation is less promising because here, even when we have no field, we know that it's NP hard to generate approximate samples. So yeah. And for the ferromagnetic Potts model, that's it's going to be our main model of focus today. So remember, for the ferromagnetic Potts model, we need at least 3 spins. The situation is much less complete, right? We have a much less understanding of what's going on with the sampling problem. We know that there is a fast sampler when beta is below some constant is the so-called Debruchin uniqueness constant that is a function of the maximum degree of the graph. But we also know that above a certain threshold, the problem becomes bizarre. So it's hard to generate samples for beta above a certain threshold. And in this window between the Debruchin uniqueness and the order disorder phase transition, which is this big critical point, we have some conjectures, we have some algorithms for some special cases, but it's in general an open question. Okay, so this is a quick primer on the sampling problem. The second problem that is going to be relevant to this talk is counting, but in a sense, this is equivalent. It's going to be more or less equivalent to us to the sampling problem, because we mostly will be focused on the approximate question. We want to understand approximate sampling, and it turns out that there are polynomial time reductions between approximate sampling and approximate counters. And this goes back to the work of Jerome, Valiant, and Basirani, and this holds for many models, including the models that we're going to be talking today. Okay, so that's counting. By the way, just what this means is that if another way of thinking about this is that if we have Hardness results for counting, they apply for sampling and vice versa. Right? Okay, so the third problem, and this is a problem that is more relevant to the theme of this workshop, is the structural learning problem. And here we're given sampling access to the Gibbs distribution, and we hope to learn the graph G. And we now have an algorithm for this problem, right? So given samples, we can learn not only the graph, but also the parameters. We can also learn beta and learn H. There are many works that led to this result, but now we have this algorithm that works that is exponential on the sparsity of the model times n squared log n. N is the number of vertices, and the sparsity of the model is essentially the max degree times the maximum value of beta in absolute value times plus the maximum external field also in magnitude. Okay, and this result is tight. More or less tight. There is a machine lower bound due to Tharaman and Wainwright in 2012. Okay, and this is a problem that many folks in the audience have done very nice work on, and hopefully I don't. I try to put the most significant results here, but if I miss any, I apologize. But this is some of the work on structural learning that led to this type result, right? Or some variations of it. Okay, so finally we get to identity testing. So this is the slightly different problem, and this is going to be truly our focus. So here I'm going to define it slightly informal. I'll be more formal in a couple of slides, but we have the specification of a model. So we got this model M, and by specification means that we have all the edge weights, vertex weights, the graph, everything. And we're given a sample access to a hidden distribution M star. Here we don't get to see the model, but we get to see IID samples from the model. And we want to verify want to say whether this hidden mole is equal to the visible mole, or they're far apart in total operation distance. Okay, so some non-results for this problem. So the most relevant one is this work by Daskalakis, Deikala, and Kamath, where they essentially show that if you can efficiently sample from the visible mole, then there is an efficient algorithm for identity testing. Okay, and as a corollary of this is, for example, since we know how to efficiently generate samples from the ferromagnetic incident mole with a consistent field or with no external field, then we get an efficient tester for efficient identity tester for the ferromagnetic incident mole. And here by efficiency, we mean polynomial running time. That's when I say efficient throughout the talk, I will mean polynomial running time. Okay, and this result here, one way of thinking about it is that this is reduction. That says whenever sampling is easy, then testing is easy too. Okay. There is another simple reduction that comes from reducing structural learning to identity testing, right? Sorry, not the reduction, but essentially if you have an efficient structural learning, then you can efficiently test, right? And this is natural, right? Learning should be a harder problem than identity testing. And the idea is that you can use your learner to learn the hidden mole and then just compare where the hidden mole is equal to the visible mole or not. Right? This is a very inefficient way of doing the testing. Okay, but recall that we have an structural learning algorithm, say the algorithm of Fly Omega. Now we have others that can do this task of learning in exponential on the sparsity times n squared log n. So in particular, when the sparsity is bounded by log n, we end up with a polynomial time testing algorithm. Okay, and here is a conjecture of my collaborators and myself after studying the hardness of this identity testing for a spin system. We started to get this vibe that whenever sampling and structural learning are hard, identity testing is also hard, right? And the one side of the implication is clear, right? When we can sample, we already know that we can test, and if we can do structural learning, we can also test. And this talk and this line of work is trying to understand the other direction, right? So in cases where we know that sampling and structural learning are hard, we want to show that identity testing is also hard. Okay. So before I state some of the results, let me just give you just a slightly more formal definition of identity testing. And in general, we're going to be doing identity testing on a family of models. So for example, we can consider the class of Q state Potts model on n vertex graph of bounded degree by D, where the edge interaction are bounded by beta and in absolute value, and the external field is bounded in magnitude also by H. Now the problem becomes given a model from the family, if this is a visible model, and sample access to some other model in the family, we want to distinguish probability constant, at least 3/4, where the modes are the same or where they are far apart in total operation distance. Okay? And we're going to substitute from now on this sparsity parameter of the model. We're going actually to break it down and write it as beta times D plus H. Beta is the max interaction strength, and this is the maximum degree, and then you have the field. Okay. Okay. So this was our first result in this line of work. It's from last year, but we look at the problem of identity testing for the anti-ferromagnetic incident mode. Remember, the ferromagnetic case we more or less understand. This concern the anti-ferromagnetic case, and we showed that when beta d was literal omega of log n, this means that essentially beta d over log n goes to infinity. So this is growing a little faster than log n, and there is no external field. Then we have no no efficient identity testing algorithm unless RP equals NP, right? So yes, so remember that when beta is order log n, we have an efficient tester. So this is getting quite close to the threshold, right? So we can put here any slowly growing function times log n, and our result will hold. RP, it's randomized polynomial time, and in the notation from the previous slide, essentially here we're showing that identity testing is hard in this subclass where we have no external field, only 2 spins. And in addition, we only consider graphs where all the edges are negative. So these are antiferromagnetic modes. Okay? So this was the first evidence that this conjecture might be true, but it was just a point, one data point. So in this work, we provide more evidence to this conjecture, and we do, I think, we do give more evidence in a more systematic way, right? Because I think we now give kind of a recipe for showing this type of Hardness results. Okay, so our result here concerns the ferromagnetic Potts model. Again, we have to assume that this is a natural assumption that beta times this is omega of log n, q has to be at least 3, q equals 2 is the easy model. And since this is a Hardness result, this is even more interesting when you have no external field. So we take h equals 0. And for this type of model, for this family of models, for ferromagnetic Potts model under these conditions, we show that there is no efficient identity testing algorithm unless there is an FP RAS for chart Bs. Okay? So this is the B's Hardness of the identity testing problems for ferromagnetic Potts model. Remember that chart Bs is the problem of counting independent sets on bipartite graph. And also, this is tight in a sense that somewhat tight, because when beta is order log n, then the structural learning algorithm kicks in and we can solve this problem via structural learning. Okay, so I'm going to now give you the proof overview, but maybe it's a good time to pause and ask if there are any questions about the framework.
Yeah, I have a super quick question for you, Antonio. So when you say structural learning, you're allowed to have very weak edges, right? But do you not care about those? Or are you assuming that all the edges have strength of beta?
So where in particular, like, okay, so when beta D, oh, I see. So you're saying like, I'm only assuming that beta D is order log n, but you could have very weak edges.
You could have very weak edges, which would then be hard to learn, but maybe that doesn't matter for your application, or just for the testing application.
Right. I think we don't deal with those in the sense that when we prove Hardness, we don't put those edges in there, right? For the Hardness result, I guess your question is for the reduction of using the structural learning for testing, right? That's
yeah, exactly. So this, I guess, this is just, you're saying this is true in a regime that's comes up against the Hardness result. It doesn't necessarily fill out the whole space.
That's right. Yeah, that's right.
Okay, cool. Perfect. Thank you.
There's another question, but I cannot access it. So
okay, the question is, can you explain more on how structural learning implies efficient identity testing?
Right. So I guess this is related to the current question. My non-expert view on this is that it's a little, what I'm saying, I guess I'm being loose when I say structural learning, because you truly need to do structural learning and parameter estimation. So if you can learn the graph and learn the parameters of the hidden model, right? You learn the graph and the parameters of the hidden model, then you can check whether this matches or is close to your visible guess, and then you can produce an answer on whether the visible and hidden match. At least that's That's my understanding of how you would do it.
I think that's a fair answer.
Yeah, I think it was that you learn in TV in the end, right? And also the sample complexity you stated, the n squared log n is indeed for parameter for learning in TV. Like, yeah, like, that's right. So you don't use a structure by itself. Yeah, I agree.
Yes, you need the parameter estimation, and Cliven's mega algorithm gives you both, right? Gives you the graph, and you can also estimate the parameters. And in general, at least for easy in pod system, structured learning seems to be the main obstacle. Once you have the graph, then estimating the parameter, it's, I will say, easier, but it seems doable. Sometimes at the same time, right? You can do both at the same time. Any other questions? Okay, so yeah, let's move on now. I want to give you a little bit of at least a full picture actually of the ideas in these proofs in the second for the pod small, and essentially it's going to be a reduction from approximate counting to identity testing, right? So we have these problems in sampling and approximate sampling, approximate counting that we know they are hard. Sometimes NP hard, sometimes RB is hard. And we're going to use an identity testing algorithm to solve those problems, right? And this will imply the hardness of identity testing. In particular, for the ferromagnetic pod small, we know that sampling and counting are RB is hard, and this is what we're going to use. This is the hardness that we're going to infer for identity testing. But I want to make here a point that there is an important difference in this proof compared to previous work, for instance, for antiferromagnetic Ising mole. And this is because when we prove the hardness for the antiferromagnetic Ising mole, we do a reduction from max cut, right? We use the tester to solve the max cut problem, which is this is a hard problem, so you get NP hardness for identity testing. But this is because if you look at the antiferromagnetic mole and you look at a thing called the ground states, which means these are the configurations with the highest probability, you see that the antiferromagnetic Ising mole, when interactions are quite strong, is going to be supported mostly on the max cuts, right? So there is this connection between the ground states of the mole and a well-known hard optimization problem. But if now you look at the ferromagnetic pod small and you look at the ground states are completely trivial. So the ground state for the ferromagnetic pod small is just the monochromatic configuration. It will be the highest, will give you the highest probability. So you don't have this hard optimization problem in the background that you can use in the reduction. And that's why for the pod small, we need to start from scratch. And in this particular, we prove the reduction from approximate count. Okay, so there are going to be two key gadgets in our construction, in our reduction. And the first one is going to be the ferromagnetic pod small on the complete graph. And this is known as the mean field model. And the second one is the ferromagnetic pod small on a random bipartite graph. So here, the second one, it's going to be a degree reducing gadget that has been used before in other hardness of approximation, hardness of counting results. Okay, so let me tell you a little bit about the ferromagnetic mean field. No, it's a tycoon. It should be ferromagnetic mean field pod small. So here, the underlying geometry is going to be the complete graph. So there is essentially no geometry, right? So we're looking at the pod small on the complete graph. And because of this lack of geometry, we can think of the configurations as just a vector in CQ, right? So the first coordinate will tell you how many vertices are red, second coordinate, how many vertices are blue, and so on, right? So this model has a very interesting phase transition. So when beta is below some specific threshold that we know what it is, it's a function of Q. The measure is going to concentrate around this uniform vector, where what this says is essentially that if you draw a sample from the distribution, it's going to be, you're going to have roughly the same number of colors, of vertices with the same color. So you're going to have the same number of, for example, here you have the same number of blue vertices, the same number of green, and the same number of red, right? And you're going to have a good concentration around this type of configuration. But when beta is above this threshold, this phase transition threshold, now the measure is going to concentrate around the majority vectors, right? So these are going to be vectors that correspond to configurations that look like this. So you have probably, it could be blue dominant, right? And then this would be a large fraction. And then the remaining is going to be equally distributed among the other colors. So you have mostly blue, and then green and red will be about the same, or mostly green or mostly red. So the vectors are going to look something like this: theta lines m, this is going to be the majority, and the rest is divided equally, right? So we're going to have some concentration on here. The constant theta, we know what it is. It's a function of Q. Okay, it's the root of some equations and depends on Q. Okay? So we have this phase transition. This is well known. It's a very well studied model. What we're interested in, what is going to be more important to us is what happens exactly at the critical point. Right now we set the parameter equal to the critical threshold. And here, when Q is greater or equal than 3, we're going to have this phenomena called phase coexistence, okay? And what happens there is that you have phase coexistence between the two possible phases, between the ordered phase and the disordered phase. So what I mean by that is, with if you draw a sample from the distribution with the critical temperature, with the critical interaction, you're going to get, with say some constant alpha, this is some constant dependent of the size of the graph, you're going to get a disordered configuration concentrated around the concentrated around the uniform vector. But with probability 1 minus alpha, you're going to get one of the three, mostly blue, but mostly green or mostly red, when there is one dominant color, right? So this is called phase coexistence because you can have these very different behaviors at the critical points. And this is a property of the Potts model only when Q is greater or equal than 3. The mean field Potts model only when Q is greater or equal than 3. For the easy mode, we don't have this type of phase transition, right? So this matches what we know, that for the ferromagnetic easy mode, testing is hard. So we couldn't push our reduction for the easy mode just because you don't have this type of behavior at the critical point, which is crucial for us, right? This is going to be our crucial gadget. Okay. So just to insert some notation here, remember that C is the partition function or normalization constant for the case of the complete graph on m vertices. We're going to use Cm. It's just the sum of all the weights of all the configuration. And it will be convenient for us to split the contribution to this partition function, think of the contribution to this partition function in terms of the majority configurations, and majority configurations are going to be this type of configurations, or disorder configurations, which are going to be this type of disorder configurations, or everything else, right? I'm not going to give the precise definition, but you can think of this is a summation that includes all the configurations that are close to, whose signature is close to this type of vectors, where the disorders are the vectors that are close with some notion of closeness to this type of vector. Okay. One easy thing to prove is that when we're in this critical regime, the contribution from the configurations that are not either close to this or close to this is very small, and we are going to more or less ignore it. Okay, so only these two types of configurations will contribute to the partition function. Okay, so this was a summary of either well-known results or results that are folklore and people know have not been written and whatever about the ferromagnetic Potts model. what we need is this very specific manifestation of this phase coexistence phenomena, is this property that says that for any R, any reasonable R, we can pick a value of the parameter beta, so that if we look at the ratio of the majority partition function and the disorder partition function, it is going to be roughly equal to R. Okay, so right, this is going to be important for our reduction. So let me just emphasize what this means, right? We know that when beta is exactly equal to beta critical, we know that there is, if we look at this ratio is going to be some constant. And what this says is that I can move in either direction from the critical point, either a little bit larger to make the majority more dominant, or a little bit smaller if I want to make the disorder more dominant. And I can do that in a systematic way and actually make this ratio equals to any desired R that I want. Okay? There is also a continuity here. It's the continuity of the partition functions is also important. Okay, so this is going to be the key property that we're going to use in the reduction. This was kind of a new property, but it's really not, right? It really follows from what was known about the behavior of the mean field mode. Okay. Okay, so here is our construction of the visible mode. So we have a hard counting instance. This is, say, a graph, and we also have some edge weight. This is the graph where we don't know how to approximately count. And what we do is that we put this very big mean field reservoir here. So we put a complete graph here, and we're going to think of M, of the size of this graph as being much larger than the size of this graph. And we're going to connect it with a complete bipartite graph. And the intuition here is that because this graph is much larger than this one, right? When this graph is in the majority phase, when you have blue dominant color here, that is going to overwhelm the whatever the distribution here is saying. So whenever you have a dominant color here, this graph here is going to be essentially the interactions here are going to be relevant, and this graph G is going to align with the other big graph, right? But when this graph now is in the disorder phase, right? So when you have roughly the same color, the same number of vertices in the same color, from the point of view of this graph, is as if this graph is not there, right? Because each vertex is going to see roughly the same number of red, the same number of blue, the same number of greens. So it's not going to feel the effect of this big graph there, right? Because it's going to cancel out. Okay, so again, when this one is in the majority phase, it's going to completely overrule what is going on G, and it says you're going to align. But when this one is in the disorder phase with mostly the same number of colors, then G will actually say how the distribution of the whole visible mode looks like. Okay. Right. So just to put in symbols what I was saying with words, essentially, when this guy is in the majority phase, and now we look at the partition function, for the visible mode, fraction of the partition mode that corresponds to the majority phase here is going to be given essentially by the majority phase of the complete graph times some constant, right? And that's because there is going to be very little fluctuation here. This, as I said, this one is, the constant is just going to be the contribution of all the edges here and all the edges here, right? Because this guy is going to align with this is going to be blue just like this one, and we can account for that contribution on A. Whereas when this guy is when the complete graph is in the disorder phase, now we do have the contribution from G, right? So the partition function for M, for the visible mode, corresponding to configurations that are disordered on the complete graph, is going to be given by the partition function on the complete graph here times the partition function of G. and some constant that now it only accounts for the edges going across it. Okay. Now, if you remember our main fact concerning the mean field model, it says that we can, for every desired R, we can make this ratio, right? CM majority and CM disorder to match that R. And using that, then we can actually find, for any R, we can find a beta M, a parameter on this side here that makes this ratio equals to this R. Right? And this is essentially crucial to our reduction, because what we're going to do, instead of doing this reduction from approximate counting to identity testing, we do this reduction from decision approximate counting, which approximate counting can be reduced to this version, this decision version, just by binary search. But essentially, it suffices to give an answer to distinguish between these two cases of giving R whether CG is whether the partition function of G of the Hardness is much smaller than R or much larger than R. So if we can distinguish between these two cases, that's enough to solve the original approximate counting problem. So it's enough to do a reduction from this version of the problem to identity testing. And if you look at this fraction that we have here, you notice that, okay, we are given an R that is going to be our desired approximation, and we can find a parameter beta for the complete graph of the reservoir that makes this roughly equal. And then all that we need to do is distinguish whether this ratio is small or large, right? Because if this ratio is small, that would mean that CG has to, the partition function for G has to be much larger than R. But if this ratio is large, the opposite happens, it has to be small, okay? So this is all our identity testing algorithm. All that it needs to give us is whether the signal that it has to give us is whether this ratio is small or large, okay? And for doing that, we create the hidden model in a specific way. So what we do is we put a complete graph here now. So this is a kind of a new model where instead of having a hard graph here, we put something that is completely trivial. And this has the benefit that, well, one of them is that we can very easily generate samples from this hidden model, which we need to do because this is what the tester the tester needs. And the other thing is that this model is always going to be monochromatic here, right? It's going to align to whatever is going. So it's always going to be monochromatic, and in particular, when this big graph here is monochromatic, this one is going to align, right? So yeah, so it's exactly the same, except that we put a complete graph here. So to finalize the reduction, remember that we only need to distinguish between very small. We only need to distinguish between these two cases. Either the partition function is much smaller than a given threshold or much larger, and this reduced to checking whether this fraction here is small or large. And what we do is that we send to the tester the visible mode that we constructed and samples from the hidden mode that we constructed. Okay. So so the tester is going to give us the two possible answers. It's going to say yes, in which case it means that it accepted the samples of the hidden mode as samples of from the visible one. But we know that the visible it's only monochromatic. The graph G, the Hardness, become monochromatic only when we have a majority domination over the disorder phase, right? So the fact that the tester says yes is saying that, well, the first thing that it's saying is viewing the visible and hidden mode as being closing to the variation distance. And if they are closing to the variation distance, this means that this portion of the construction, this one here, has to be monochromatic in both. And that only happens when you have majority domination on this side. So in that case, since the majority dominates, we can say that the ratio is large. Otherwise, when it's no, then the total variation distance is going to be large, and that means that the distorted phase dominates, right? Because now this means that in the hidden mode here you have monochromatic, whereas in the visible there you are behaving like what you see is whatever G, the hard instance, it's saying that you should see, right? So in that case, the ratio is small. Okay, so that's reduction. Hopefully the main idea of the reduction is there. Hopefully you got some insights. Remember that essentially we use the identity testing algorithm to solve a bizarre problem. So this implies the hardness of identity, the big hardness of identity testing. But we are not done, right? if you see our construction, the degree is blowing up, right? The degree is large. We have complete graph, much larger than the actual hard instance, so polynomial degrees in general. The good thing is that beta, the strength of the interactions, is we kept it constant. We don't have to do anything with that, but definitely there is this problem that the degree is unbounded. But this can be fixed, and for this we use a general strategy also from results proving hardness of approximate counting for various problems. And the idea is that we generate a random bipartite graph, random regular bipartite graph, and we replace every vertex in our previous construction by one of these random bipartite graphs. Right? And then we use some of the available degree to connect the internal. I mean, we do, like, let's say epsilon d of the okay, some fraction of the degree. We use it to connect the graph internally, but we leave some degree free to actually connect the vertices. Okay, so doing this, we can dilute the degrees of the previous construction, right? So if you have a vertex that have a very large degree, then essentially you can connect to many of these new vertices in the random bipartite graph that we put in. So in order for this to work, we need these gadgets to behave like vertices. And essentially what we want is that they are monochromatic, regardless of they're very close to the ground state, regardless of the influence that comes from the outside. We want these ones to be mostly red, mostly green, mostly blue, because a vertex will only have one color, and the dominant color in this gadget will essentially be the color of the vertex. And this follows from two things. The first one is that the random bipartite graph are good expanders, but also that beta d, our parameter, this sparsity parameter is at least omega of log n. Okay. So this is back, just to conclude, this is the initial conjecture, or our working conjecture, that whenever sampling and structured learning or structured learning / parameter estimation are hard, then identity testing is hard. In this talk, I verified the conjecture for the ferromagnetic Potts model. Earlier work did for the antiferro easy model. And also in this work, and just as evidence that this approach seems kind of robust for proving this type of results, we're able to show similar result for RBM. So essentially, we proved that for RBMs, whenever sampling R learning are hard, then we also get hardness of identity testing. Okay. Thank you.
Cool. Yeah, very nice reduction. Thanks, Antonio. So if anybody has any questions, feel free to speak up. I guess there were a number of questions during the talk. Do you mind saying something briefly about how the RBM case differs, and what is the key idea or the key gadget in that case?
So the gadget is a little different. The intuition behind it is not, because it also relates to this phase coexistence phenomena. So once we have this phase coexistence phenomena, we do some gadgeteering to actually derive the result. It really have the same structure, but at the moment, this is why we don't have a generic implication that hardness of approximate counting implies hardness of testing or anything like that. There is a step of the proof that is the construction of this gadget based on the phase transition, on the phase coexistence. So for RBMs, our constructions are a little simpler. The reservoir, instead of having a complete graph, we actually, well, I wouldn't say simpler. Yeah, let's say they are different. We do a different construction outside of the hard instance, and we use that in a very similar way to answer yes or no to this question of whether the partition function is above or below some threshold. So cool. The flow of the proof it's the same. What changes is the the specific gadget that we have to put to capture this phase coexistence. But that seems to be what's, so the phase coexistence is what drives the hardness of sampling and count. Right? This first order phase transition is what implies the hardness. And it seems that there is some connection here, but it's not completely fleshed out. Yeah.
One question, so when, so for the tolerant identity testing question, so you're trying to test whether the two models are close versus far. Do you expect, I mean, the reduction to be easier or better reduction? Because I think in that case, it's also easy when both sampling and structure learning is easy. So you can approximate the distance.
Well, so in this case, you're saying that sampling and structural learning are easy?
No, I mean, I'm saying if sampling and structural learning are doable, then I think you can also approximate the distance.
Right.
You can
do
tolerant testing, but I expect the hardness will be easier to prove for the stronger question of approximating the distance. So have you guys thought about this?
Oh, I see. So if you look at the, yeah, I've thought a little bit about, say, proving hardness of approximate the structural learning, and seeing this, there are experts in the audience that can probably answer this better. The computational hardness seems open for some very simple cases. So yeah, I don't know if it's going to be easier or harder to prove, but it's definitely an interesting. There are definitely interesting open questions there.
Cool. Thanks, Antonio. Thanks everybody for attending, and look forward to seeing everybody tomorrow for the last day of the workshop.
Thank you.